Greetings, fellow mathematicians. We're going to take a look at a really simple differential equation, and we're going to solve it with Laplace transforms, so that way you can understand how this method works. Now I want to put this right at the beginning. You do not want to solve this differential equation with Laplace transforms. It's going to be a lot more work for this problem. Let's point out why. We have constant coefficients and a very simple non-zero right-hand side. We can find the particular solution very quickly here. So if you take a look at that, your right-hand side is a constant. You would try as your particular solution, yp equals a constant a. And if you differentiate that first and second times, those derivatives become 0. Plug that in, and you should be able to find here by plugging that in, you get negative 3a equals 1. So you should find yp comes out to be negative 1/3. Now again, other methods are going to be a lot faster, and that's not the point of this video. The point of this video is to show you step by step how to use Laplace transforms to solve this. Now we should find this somewhere in the end once we go through Laplace transforms appearing in our answer. And let's go ahead and get started. Step 1, we're going to take the Laplace transform of the entire differential equation. So let's write that out. Any constants I'm going to pull in front of the Laplace transforms since this is linear. So we'll get the transform of the second derivative. We're going to have minus 2 times the transform of y prime. We're going to get minus 3 times the transform of y. And this is worth emphasizing right now. I find even some of my best students miss this. Don't forget to take the transform of the right-hand side. What you do to one side, do to the other. Take the Laplace transform of both sides. So this comes out to be the transform of 1. Now, again, you want to calculate all these transforms using your Laplace transform table. We have the partial results that we're going to need right over here. And let's go ahead and take it term by term. And where you use your initial conditions, unlike direct methods where you use them at the end, we're going to use the initial conditions in the transforms of the derivative and second derivative, right here at the end in both those expressions. All right, take your time with this and be careful to use lots of parentheses. We have minus 2 and minus 3 in front. Typically, any negatives in front with subtractions, you're going to want to use parentheses. So let's go ahead and write down the transform of the second derivative. That's going to be s squared times f of s. F of s, that's your Laplace transform of y. We then have, for the transform of the second derivative, minus s times the function initial condition, which is 1. So this term looks like that's going to come out to just minus s times 1, so minus s. And then we have minus the derivative initial condition, so minus 2. All right, now we go to the transform of the first derivative. We have a negative 2 out front. Use parentheses, and your transform of the first derivative, that is s times f of s. And then minus your function initial condition, which is 1, so minus 1. All right, and don't overlook this part, the Laplace transform of y. That's just our definition of how we understand what f of s is. So this last term here is just going to be minus 3 times f of s. All right, that's your transform of the entire left side. Now we need the transform of the right side. The Laplace transform of 1, that's really simple. You can look that up in your Laplace transform table. That comes out to 1 over s. It's probably one of the first entries in your Laplace transform table. So our right-hand side transforms to 1 over s. All right, now that's basically step one of using Laplace transforms. Here we have now an algebraic equation, and we're going to solve it for f of s. So let's take our time. I'm just going to go ahead and distribute this -2 through the parentheses, and I'm just going to write down all the terms here. It's okay if you want to go through and do multiple steps together, but I find even myself in class, if I do that, I'm going to screw up and make some mistakes. So let me take my time. We'll have s squared times f of s minus s minus 2. Now we're going to distribute and get minus 2s times f of s. We're really going to have plus 2 there. All right, and then we have minus 3 times f of s and equals 1 over s on that right-hand side. All right, we can probably see we have some terms that we can combine together. We have a -2 and +2, which we can cancel out. And what we have are a bunch of terms multiplying f of s. So if you want, you can think of with this first, this middle, and this term at the end, combine them by factoring f of s out. And it looks like what we would have is your coefficients, s squared minus 2s, and then minus 3. And that is all multiplying f of s. And we should have some other terms here. We have this minus s still on the left side. And I believe that's it from your left-hand side. Your terms that were left over either got combined by factoring f of s out, or we just have terms involving the s variable. That equals 1 over s. And now we can solve this for f of s. That's your solution in the frequency domain. Let me go ahead and add s to each side. And this is where it's worth mentioning a few different tips, tricks, or things to look for. Now, one, I guess, observation that you can kind of check some simple mistakes with. All the stuff that's multiplying your f of s, that is exactly the characteristic equation for the left-hand side of that differential equation. And that's not a coincidence. So this should transform to s squared minus 2s minus 3. Earlier, you would have used the characteristic equation with r as the variable, but now it comes out to s. There is a connection, but we'll save that for another video. The other thing I want to mention right here is a tip for the more difficult problems. Sometimes you actually want to combine this together, like we have two separate fractions here. You might want to combine them together like we will. There's going to be some problems where you might be able to save yourself a little bit of work with the algebra in doing a partial fraction decomposition by leaving this as separate fractions. Here, I'm going to go ahead and combine these together. Just use a common denominator and think of that as s squared over s plus 1 over s. And if you go ahead and add them together, we're going to keep our left side the same for right now. We're going to combine the right-hand side as a single fraction. We can write that now as s squared plus 1 over s. And we can very easily now solve for f of s. That's your solution in the frequency domain. We're just going to divide by this stuff multiplying f of s. So it looks like what we get for our solution in the frequency domain, we're going to have s times s squared minus 2s plus 3. Your factor here divides over. Don't forget that factor of s in the denominator on the right-hand side. And your numerator of that should be s squared plus 1. All right, that completes basically step 1 and step 2, transforming and then solving for f of s. Next, let's go ahead and get to the algebra so that way we can rewrite this to match Laplace transform pairs. Next up, the partial fraction decomposition. This is where most of the work occurs for this problem. As always, you want to fully factor your denominator, and you can factor this s squared minus 2s minus 3 as s minus 3 times s plus 1. Now this falls into the easiest case for a partial fraction decomposition where you have distinct or different linear factors. So let's go ahead and write down the partial fraction decomposition. We have three factors, s minus 3 times s plus 1, and our numerator is s squared plus 1. Since we have linear factors, each of our partial fractions will look like a constant over each of the linear factors. So term by term, looks like we should get a over s. We'll go with b over s minus 3. And then c divided by s plus 1. All right, you know what to do from here. We're going to clear fractions, and if we do that, multiplying both sides by that LCD, looks like we should get s squared plus 1 on the left side. And when you multiply that LCD over here, all your denominators should cancel, leaving you with, looks like we'll get a times s minus 3 times s plus 1. We're going to have now b. The s minus 3 is going to cancel here, so we're going to have b times s plus 1. And then your last term involving c, looks like we should have the s plus 1 term canceling, leaving us with c s times s minus 3. All right, since we have linear factors, we can choose nice values for s and plug in. So it looks like we'll want to go with, let's say, s as 0. What else would we want to go with? Let's say negative 1 and positive 3. All right, and let's just take it one value at a time. We're going to plug s as 0 in everywhere. You would have did this earlier in your Calc 2 course, but instead of s, you would have had the variable x. So plug in s as 0. Looks like we should get, on the left, 1. And looks like your b and c terms will drop out. And when s is 0, looks like we're going to get minus 3 times 1. So we'll get minus 3a. And that immediately tells us that a is negative 1 over 3. All right, we have two more. Let's go ahead and plug in s as 3. 3 squared, 9 plus 1, that'll be 10. And just be careful here now, s as 3, your s minus 3 factors will become 0. 3 minus 3 is 0. So it looks like your a and c terms are gone, but now the b term remains. We're plugging in s as 3. So it looks like we're going to have factors here of 3 and 4. So it looks like we'll get, on the right side, 12b. And you can go ahead and divide 12 over, cancel out a common factor of 2, and you should find that b comes out to 5 over 6. All right, last value, we're going to plug in s as negative 1. Just be careful with your signs. Negative 1 squared is positive 1. That left side is going to become 2. And now anything with the s plus 1 factor will evaluate to 0 or cancel out. So your term with a is gone, and likewise your term with b That's gone. You should only have now c remaining. And just be careful here, s is -1. I'm going to be careful with my signs because, again, in class, I would probably screw this up. So we're going to get -1 times -1 minus 3. And that looks like that's going to be +4 when you multiply that out. So on our right side, we're going to have +4 times c. And divide by 4, and you should find c comes out to +1/2. All right, and that is the work for your partial fraction decomposition. And we're going to go ahead and plug in those values here to your partial fractions. Now, we have basically reciprocals, powers of s, or factors of s in the denominator. Let's not plug the fractions into the numerators. Let me pull them out front instead. Now, this is going to be how we rewrite f of s. We now have rewritten f of s in terms of its partial fractions, and all three of those partial fractions match existing Laplace transform pairs. So let's go ahead and write this down. This is almost all of your work. We're just going to plug in here. We have a as -1/3. I'll rewrite this first partial fraction as -1/3 times 1/s. Next, we're going to plug in our value for b, which is 5/6. I'm going to pull that fraction out front, so we'll write that as plus 5/6 times 1/s minus 3. And then your last value for c, we had that as 1/2. We'll pull that out front again and write this last partial fraction as plus 1/2 times 1/s plus 1. All right, now this problem, the f of s requires no more additional algebraic tricks since all three of those partial fractions match existing Laplace transforms. All right, so we're just going to go ahead and do the inverse transformation by matching here. We're going to match 1/s on the f of s side. That's going to match back to the time domain as 1. So if you do your inverse transformation, we're going to have our constant -1/3. And then that multiplies the inverse transformation of 1/s, which is 1. All right, next we have our constant 5/6. And now when we do our inverse transformation, we're going to match it with this Laplace transform pair, 1/s minus a. And if we identify the value of little a, we're just going to be using it right now as 3. So when you transform back to your function of time, you should get e to the 3t. So we get, as our inverse transformation for that partial fraction, 5/6 times e to the 3t. And then your last one, we're going to use the same Laplace transform pair, but now since it's s plus 1, we're going to think of little a as being -1. And that's so we can match it properly with the given Laplace transform pair here, 1/s minus a. So just go ahead and match that back, where little a is -1, and we should get as our last part of our solution 1/2 times e to the -t. And that is basically it. So if we go ahead and write down our solution, we don't need that multiplying by 1. And again, the multiplying by 1 came from the inverse transformation of 1/s. Here's our solution. And I'll write it down in 2 different ways, depending on the independent variable that you're using in your differential equations course. We first get as our solution y equals -1/3 plus 5/6 e to the 3t and then plus 1/2 e to the negative t. Your course might use t as the independent variable. I usually stick with x as the independent variable in my differential equations course. It doesn't matter though, so if we write this down in the other standard way, just replace all your t's with x and we get the same solution just with a different independent variable. All right. Now, again, just to review from what we mentioned at the beginning, for this problem, you do not actually want to use Laplace transforms to solve this. If you can, if your question on an exam or homework is open-ended, use any method, you would actually want to use undetermined coefficients, since that right-hand side is very simple. Go back to the beginning of the video, you might recall we mentioned that the particular solution comes out to be a constant, and you can very quickly solve for that constant, which would be negative 1/3, and you can see that appearing in your solution here. Also worth mentioning, with this as our first problem on solving differential equations with Laplace transforms, the other part here at the end, those two exponentials, that's your complementary solution, and we've already solved with Laplace transforms for the values of C1 and C2. Basically, Laplace transforms solves and does everything all at once in exchange for a fair amount of algebra. Hopefully you enjoyed this video going through step by step how we solve a differential equation with Laplace transforms. We're going to have some other videos on more complicated problems where Laplace transforms actually might be a little bit less work. If you enjoyed the video, leave a comment below, and also don't forget to like and subscribe.